All right, so let's take a look at an example that's similar to what you have in the homework when it comes to those impulse response problems. So what I gave you were pole zero plots. Those pole zero plots look like this. Here's the real, here's the imaginary. All right, and I said that I had, let's say I have a set of complex conjugate poles. Okay, and let's say this is minus 6j. Okay, and let's say I've got a 0 at the origin. Okay, now what we said in class the other day, poles are the things that make the denominator equal to 0. All right, the roots of the denominator. Zeros are the roots of the numerator. Numerator. All right. So basically things that make the numerator, can't write here, numerator equal to 0. All right. So this guy makes the numerator equal to 0. These two make the denominator equal to 0. The way we write that is I say, well, clearly if s equals 0, the numerator must be just s, because the value of 0 makes the numerator 0. Okay. On the bottom, it looks like minus 5 minus 6j makes this guy equal to 0. And down here, also minus 5 plus 6j make this equal to 0. Now, I was saying that backwards the way I was writing that, but let's take a look. If I look at what are the roots of the denominator here, all right, the value that makes this term, so we say s plus 5 plus 6j equal to 0. What value of s is it? It's minus 5 minus 6j. And here, s plus 5 minus 6j. What value of s makes that 0? We say it's minus 5 plus 6j. Okay? So be careful about the way I write those roots, right? It's the value of s that makes this term equal to 0 that is the root. Okay? All right, so for this pole 0 plot, I get that transfer function. Now in the homework, what I ask you to do is to find the impulse response. Now again, let's keep in mind what this system picture is useful for us. One of the things is we say, if I have a system, I can represent it by some system function or transfer function h of s, which relates the Laplace transform of the input to the Laplace transform of the output. Okay, so as an example system that I might have, we said, what if I had a circuit that looks like this? Here's C, here's R. All right. Let's say my input is the input voltage, and I'm just going to write it as x of t. Let's say my output is the output voltage y of t. So in this case, x of t is V in, y of t is V out. Okay. The way I can write that transfer function is I can say x of t equals rc dy dt plus y of t. Again, if I remember that x of t is V in and y of t is V out, this basically came from KVL, right? So by Laplace transform, I can say x of s equals src plus 1 times y of s. Okay, we rewrite that and say y of s over x of s, which is our transfer function h of s, is 1 over src plus 1. Okay, so that y of s is equal to h of s, x of s. Okay, so what we have, and that's what this picture up here told us, right? The Laplace transform of the output is equal to this transfer function, which tells us something about the system's dynamics. the Laplace transform of the output is equal to this transfer function times the Laplace transform of the input. Okay, so and then we look at basically having different inputs around. So one input might be, I could say, what if x of t were equal to the step function? That would be equivalent to basically connecting a DC source to this guy at t equal to 0, right? Well, if that's true, x of s equals 1 over s, and I say that y of s equals 1 over src plus 1 times 1 over s. And I inverse Laplace transform to find what the response is if I apply a step to this thing. Now, the other type of input we talked about the other day was what happens if I have x of t equal to an impulse. So I basically just suddenly apply, so that what that means, remember, is that here's the impulse, right? This impulse is something that has unit area, okay? And it is equal to 0 everywhere except 1. Or sorry, everywhere except 0. So delta of t is equal to 0 for t not equal to 0. And the area under it is 1. Okay, it's undefined technically right there at the origin. All right, the basic idea is if that's my input, we say that x of s is equal to 1. All right, we worked that out. Said its Laplace transform is just 1. So if I go back to this picture right here, say for this circuit, and I said, well, my input was an impulse, then my output is just h of s in that case, okay? Which for this guy is this, okay? That's very easy for me to inverse Laplace transform. What do I know? If I have e to the negative at for t greater than 0, right? That guy becomes 1 over s plus a. This looks just like that. That means that my impulse response, which is the natural response of the circuit, if it has, so in other words, if the circuit has some energy at t equal to 0 stored in this capacitor, what's going to happen is it's just going to naturally let that decay, and that decay would be controlled by that function. All right. So, what do we want to do here? Well, what I want to do is, so for the transfer function, I guess, that we started out with at the very beginning of this lecture, where I had this pole 0 and I created this transfer function for it, I want to find the impulse response for this guy, okay? So I want to find the impulse response. So I know always that the Laplace transform of the output is h of s times x of s. For the impulse response, x of s equals 1. Okay, so I have y of s equals h of s, okay, which in this case is this guy, s over s plus 5 plus 6j times s plus 5 minus 6j, like so. Now, the question is, what do I do with this thing? Well, what I want to do is so these things are always rational functions, right? And for real circuits, we said that I'll always have proper rational functions, which means that the order of the denominator polynomial is higher than the order of the numerator polynomial. Now, why does that make sense? What we're looking at is the Laplace transform that corresponds to this natural response of the circuit, which we know is always exponentials, all right? Or it's decaying cosines, okay? Which means decaying complex exponentials. All right, so if that's true, I know that I should be able to get this into some form that looks like k1 over s plus a plus k2 over s plus b, something like that. This guy maps to an exponential, e to the negative at times k1. This guy maps to an exponential k2 e to the minus bt, like that. All right. This guy is going to map to an exponential as well, but his exponentials are going to be complex. All right, so what we got to do is figure out how we do that process. All right, so in this case, I say that this could be k1 over s plus 5 plus 6j plus k2 over s plus 5 minus 6j, like that. Okay. So I find a common denominator. Basically what you're saying is somehow I can add these two things together to get that. To do that, I have to find a common denominator, right? So I know that s over s plus 5 plus 6j times s plus 5 minus 6j has to be equal to k1 times s plus 5 minus 6j plus k2 times this guy, s plus 5 plus 6j, all over s plus 5 plus 6j times s plus 5 minus 6j, like that. Okay? All right. Now, the denominators on both sides are the same. So basically I could just forget about those. And I have to say, what do I need to do to make the numerators equal to each other? So I have s equal k1 times s plus 5 minus 6j plus k2 times s plus 5 plus 6j. All right? So how do I do this? I need to find what k1 and k2 are. So the easiest thing for me to do is to make some guesses for s. And make some good guesses so that basically one of the terms goes away. So let's guess that s equals minus 5 plus 6j. Okay? If I do that, I say minus 5 plus 6j, that's this side, equals k1 times minus 5 plus 6j plus 5 minus 6j plus k2 times minus 5 plus 6j plus 5 minus 6j. Or sorry, plus 5 plus 6j in this term. Okay? So let's look. Here, minus 5 plus 5, plus 6 minus 6. That whole term goes away. This one, however, that doesn't happen. This one I have k2, and it looks like I have minus 5 plus 5, but I have plus 6 plus 6. So this becomes 12j. So that means that k2 is minus 5 plus 6j over 12j. Now, in the end, it's going to be easiest for me to get this thing into polar form. All right, so let me figure out how to get this into polar form. All right, let's pick up where we were. Okay, so the easiest thing to get is to get this thing into polar form here. So how do I do that? Well, let's look at the bottom, right? The bottom, what I say, 12j, anytime I see a j, that tells me that this guy has an angle of 90 degrees. And the way I can see that is 12 cosine 90 plus j 12 sine 90 degrees. This term is 0. This term becomes j12 because sine of 90 is 1. Okay, so that tells me that on the bottom I've got 12 e to the j 90 degrees. Okay. What about this guy on top? Okay, so we got to find out what the magnitude is first. So square root of 5 squared plus 6 squared, square root 7.81 is what I get for a magnitude of this guy. Okay. Now I got to get an angle of this guy. Now here's where it gets tricky. Okay. It's part of the reason why I wanted to look at this. Where does minus 5 plus 6j sit? Well, it sits somewhere up here, okay? Minus 5 plus 6j as a vector sits somewhere up here. It's in the second quadrant. Arctan only gives me stuff in the first and the fourth quadrant, okay? So in this case, I say that the angle of minus 5 plus 6j, the angle of that guy, is equal to minus 180 degrees, plus whatever arctan I get from this guy. All right, so let's see. Arctan of, in this case, 6 divided by minus 5, negative 50.1944 degrees. So it was plus arctan of 6 over minus 5. That becomes, so negative 180 minus, or plus that answer, minus 230.194 degrees, which makes sense. Minus 230 degrees should be somewhere over in the second quadrant. Okay? So that tells me that this top guy becomes e to the minus j 230.194. Okay? So that K2 is the combination. So 7.81 divided by 12, 7.81 divided by 12, I get 0.651. And the angle I get, negative 230.194 minus 90 degrees. All right. So I did negative 230.194 minus 90 since it's on the bottom, so that gives me minus j 320.194 degrees. Okay, that's our K2 value. Now we got to find our K1 value. So we go back to our original expression. What did we have at the beginning? We had S equals K1 times S plus 5 minus J6 plus K2 times S plus 5 plus J6. So now I guess the other one. Let's let S equal minus 5 minus 6J. Okay? So I get minus 5 minus 6J equals K1 times minus 5 minus 6J plus 5 minus 6J. Okay, that's this term. And then over here I have K2 times minus 5 minus 6J plus 5 plus 6J. Okay, minus 5 plus 5 is 0. Minus 6 plus 6 is 0. That term goes away. This term, however, simplifies down to minus 5 and 5 kill off. Minus 6 and minus 6 becomes minus 12. So this becomes minus 12J times K1 equals minus 5 minus 6J. Alright, so let's do it the same way as before. K1 equals minus 5 minus 6J divided by minus 12J. Okay, so we'll do it in polar form again. Before I had 12J on the bottom, now I got minus 12J on the bottom. That basically means I've got 12 e to the minus j 90 degrees on the bottom. Minus 5 minus 6j, what is that? Well, where's that guy at? Vector-wise, he's down here in the third quadrant, right? So again, because he's on the other side, we say the angle of minus 5 minus 6j is minus 180 plus the arctan of 6 over 5. What does that become? So minus 150 minus 180 plus the arctan of 6/5. All right, so this guy becomes minus 129.806 degrees. Okay, So the magnitude would end up being the same on top, 7.81 e to the j, e to the minus j, 129.806. Okay, so what does K1 become? 7.81 divided by 12, we said was 0.651. I got 129 minus 90. Okay, so that becomes minus 129.806 minus 129.806 plus 90, because I got minus 90. So that becomes minus 39.806. So e to the minus j, 39.806. Okay. All right. So let's take a quick look at what we got for K1 and K2. K1 was this guy. K2 was 0.651 e to the minus j, 320.194. Okay. That is the same as 0.65 e to the, if I look at this carefully, this is the same as 39.806 degrees, right? So I do 360 minus 320.194. That becomes 39.806 degrees. In other words, negative 320.194 degrees is the same as 39.806 degrees. Okay, so these two, K1 and K2, are conjugates of each other. All right, which I mentioned in class the other day, but here we can really see it. All right, so back to our original story. That meant that our h of s becomes, with these values, K1, which is 0.651, e to the minus j, 39.806, divided by s plus 5 plus 6j, like that, okay, plus 0.651, there's been a 1 there, e to the j, 39.806 degrees over s plus 5 minus 6j, like that. All right. So now I can inverse Laplace transform these things. Okay. This guy becomes, so if I want to say what's my y of t here, what's my output, what's my time domain function? Well, it's the inverse Laplace transform of this thing. And it becomes 0.651 e to the minus j, 39.806 degrees times e to the minus 5 minus 6j t. Okay, that's the inverse Laplace transform of this, plus 0.651 e to the j, 39.806, okay, times the Laplace transform of 1 over s plus 5 minus 6j, which becomes e to the minus 5 plus 6j t. Okay, so let's play with this a little bit. What do I get? Well, I have, if I break these apart, right, I see that like this term right here, that term's going to become e to the minus 5t times e to the minus 6jt. Okay, so what does that give me? Well, I see that I have 0.651 times e to the negative 5t. Okay, I have that common in both terms, so I factor that out. And I'm going to get e to the minus 6jt times e to the minus j, 39.806 806 degrees, plus whatever this guy gives me, which is e to the 6j times e to the j 39.806 degrees. Okay. Let's use Euler's identity on this thing. Okay. All right, so I'm going to use Euler's identity on this character. And I'm going to say e to the minus 6j t. First of all, before I even use Euler's identity, I can combine these into one term, right? And I can say, let me do it this way. I can say e to the j, I'll say minus j 6 plus 39.06 degrees minus 6t, right, plus e to the j 6t plus 39.806 degrees, like that. Okay? We'd use Euler's identity on that thing. Okay? So that tells me cosine, all right, cosine of a negative angle, all right, the negative doesn't matter, right? So it becomes 6t plus 39.806 degrees. Okay? Now minus j, when I put that in the sine term, becomes minus j sine 6t plus 39.806 degrees. All right. Now this guy here becomes plus cosine 6t plus 39.806 degrees plus j sine 6t plus 39.806 degrees. So I see that the imaginary terms go away, and I'm left with 2 cosine 6t plus 39.806 degrees. So that tells me that this whole thing here, if I take this result and plug it back in up here, I get 0.651 e to the negative 5t times 2 times cosine 6t plus 39.806 degrees. All right, very similar to what I said in class the other day. Okay, so this is the impulse response. So effectively what's going on with the impulse response is I have a cosine wave that decays with time. As t advances, the amplitude of that cosine gets smaller and this guy goes away. That's kind of what we would have expected from what we know previously.